we saw the successful landing of the Pathfinders, a small robot about this big, landed on Mars, roamed around, sent some unbelievably spectacular pictures back. And it was delivered by a very interesting, entry landing system. It was a big balloon. It bounced around for a while and then opened up and the thing crawls out. It's still functional, which is amazing. I mean, if somebody had walked into my office and said, this is how we're going to deliver your $3 million space vehicle, I'd throw them out of the office. So it shows you how much I know. So anyway, we saw that happen, and we knew that there were going to be subsequent missions to Mars planned. And we said, well, how the hell are they going to communicate? And the answer was supposed to be a direct radio channel from the surface of Mars back to the Deep Space Network, which has big 70-meter dishes in Madrid, in Canberra, Australia, and Goldstone, California. So we got to thinking about that, and we said, we ought to have a richer networking environment for space exploration than point-to-point radio channels. And we said, well, Internet's a pretty good example of a rich networking environment. It works on Earth, so it ought to work on Mars, right? And we persuaded ourselves that it could work on Mars. And then we started thinking about, what would TCP/IP do if it were running between Earth and Mars? Okay, so you start doing the math. How far apart are we? Well, when we're closest together in our orbits, it's 35 million miles. It takes 3.5 minutes for a radio signal to go from Earth to Mars at the speed of light. And another 3.5 minutes to come back. This is not exactly interactive, that's 7 minutes. What about the 20-minute time it takes when we're farthest apart in our orbits, 235 million miles, do the math. 20 minutes one way, 40 minutes round trip time. You know how TCP flow control works, right? You run out of room and you say stop. And if the other guy hears this in a couple hundred milliseconds, it works great. You do a little buffering and all point. If it takes 20 minutes before he hears you say stop, he's transmitting at full speed. Packets are falling all over everywhere. Doesn't work. Then there's this other problem. It's planetary rotation. We haven't figured out how to stop that. So if you're sitting on the surface, of Mars, and the planet's rotating, and you're talking to the spacecraft, eventually you can't talk to it anymore because there's a planet in between. So we said, all right, this is variable delay and disrupted communication, and TCP is not really well suited to that. So we said, all right, let's start over again. Let's think about what the protocols would have, what parameters and features the protocol would have to have. So we developed a whole new suite of protocols that are part of what's called delay and disruption tolerant networking. The Advanced Research Projects Agency actually funded some of this work. And we said, this would be really helpful in tactical communications because you do get disrupted. Any of you using a mobile here and anywhere actually know that you don't always get good connectivity. So there's disruption just like we have in the interplanetary situation. So we developed the protocols. We went through 4 iterations of them, kind of like TCP/IP. We now have them running on ground equipment here on Earth, in the International Space Station, in the orbiters around Mars, and on the rovers, including the Mars Science Laboratory, and on a spacecraft called Epoxy that's in orbit around the Sun. And Epoxy has visited 2 comets in the last 10 years' time. So we have a nascent interplanetary backbone in operation. We're standardizing this protocol with the Consultative Committee on Space Data Systems, which is a UN organ where the spacefaring countries of the world agree on standards. If they adopt the standards, when every nation, any nation, launches a new spacecraft then that can use these protocols, then we can repurpose that spacecraft when it's done with its primary scientific mission to become a node in an interplanetary backbone. So we hope over time, over the rest of the decades of this century, that we will literally grow an interplanetary backbone in order to support both manned and robotic space exploration. The standardization is just like being able to plug into the internet and talk to 2 billion devices out there. Should I go on with one other time? This is not the end. Okay, that's sort of it sets the stage for the next big plan. ARPA released a research grant to a consortium to design and not build, but to design a spacecraft to get to the nearest star in 100 years' time. Now, the nearest star is Alpha Centauri. It's 4.4 light years away. And right now, the current propulsion systems available, it would take 65,000 years to get to Alpha Centauri. This is a little long even for an ARPA project. It's only 6 times longer than our entire civilization has existed. So one of the big challenges is creating a propulsion system that can get to the nearest star in 100 years. Right now, probably ion propulsion with enough payload on board to keep the propulsion engine going for 100 years. At the 50-year mark, where you hope you're halfway to the destination, you kind of flip over to slow down, because otherwise you go zipping through the Andromeda system at 20% the speed of light, you get one picture and that's it. So we want to slow down and go into orbit and stay there for a while. So that's the propulsion problem. There's a navigation problem, because normally what you do when you're doing interplanetary navigation is that you send a signal to the spacecraft in mid-course to make any corrections that are needed in order to make sure it gets to the destination in the proper speed and time. Well, you know, it's okay if that mid-course correction interaction has a few minutes of round-trip time delay, or tens of minutes even. But imagine you have a spacecraft a light year away. So it takes a year to send the signal to get there, to say, do something different, and it takes a year to find out what happened. So this is not exactly interactive. The conclusion we reached is we need to autonomously navigate, and that's probably okay because we know about the basic proper motion of the stars within about 10 light years of Earth. And you can use stars that are much farther away, you know, tens of thousands of light years away, because their apparent location will not change if you move a few light years from Earth. So you use them for orientation, and then you navigate your way based on knowledge that you have on board. So it's an autonomous navigation problem. This is good. We don't have to do that 2-year round-trip time thing. Then the last problem is signaling. How do you generate a signal in a spacecraft that's 4 light years away that we can detect here on Earth? And right now, a common thought is to use femtosecond lasers. This is a laser that can compress, say, 100 watts worth of power into 10 to the minus 15 seconds. This is a really big pulse. And it's something we should be able to detect from 4 light years away. There is a little problem, however. Even if it's a nice collimated laser beam, the thing is going to beam spread over the course of 4 light years. It'll be about as wide as the solar system, which means it's a very attenuated signal. The way you typically respond to a problem like that is to build a synthetic aperture receiver. So I need the interplanetary backbone to build a synthetic aperture receiver to pick up the signal and reintegrate that signal back so I get enough power to actually interpret the data that's coming back. Now, one of the physicists in the group said that there might be another interesting alternative. He reminded us that gravity bends light. That's how we demonstrated that Einstein's theory of space distortion due to gravity was correct, because there was an eclipse of the sun. I don't remember the year, but I think it was 1916. But in any case, during this eclipse of the sun, a particular star's position shifted. And we could see that because of the eclipse. And that shift was predicted by Einstein's theory. So this confirmed that there's a bending of light by gravity. Well, the consequence of that is that if you go 550 astronomical units away from the sun, which is about 55 billion miles, you are in the focal point of the sun's gravity lens. So if we could get a spacecraft to go 55 billion miles away and sort of park, that's not an exact analogy, but let's pretend we park at that lens location, we could possibly reintegrate the light coming back from the femtosecond laser in the Andromeda system, so we could actually detect it. So that's the latest plan for the interstellar system. And there's something personally delicious about all this, because the guy that started us thinking about computer networking and applications that are not just computational, things like artificial intelligence and knowledge engineering and things like that, is a man named J.C.R. Licklider, who was at MIT. And he wrote a note to his colleagues referring to the intergalactic network that he had in mind. Of course, this was all tongue-in-cheek, but he was referring to something which eventually became the ARPANET project. And because we all remember that in my community, when we developed the interplanetary protocols, we made the transport protocol the Licklider Transport Protocol, or LTP, in commemoration of his intergalactic ambition. Unfortunately, we're only able to do interstellar. Intergalactic is for the next generation to shoot.
Great. Before we